Everybody, let's have a quick discussion about center of mass. So let's start off by talking about weighted means, because I'll just tell you, center of mass is a mass weighted mean position. So let's talk about that. See, here's a number line. Okay, so let's say I have some boxes here, here, and here. Okay, what's the mean position of the boxes? Say this is in meters. Okay, so then it would be, there's a box at 2 meters, another one at 3 meters, the other one at 5 meters, divided by 3 boxes. Right, so that's the mean position. 2 plus 3 plus 5 divided by 3 boxes. Now, how about if this box over here is worth $6? Sounds weird. And then this one is worth $4. This one over here is worth $3. What is the dollar weighted mean position? So there's a $6 box at 2 meters, plus there's the $4 box at position 3 meters, plus there's a $3 box at position 5 meters, divided by 6 plus 4 plus $3. Okay, if you run this computation, what are the units that you would get? The numerator is dollars times meters. The denominator is dollars. So your answer will be meters, which is the mean position of the 3 boxes. But that is weighted by its value in dollars. So it's a dollar weighted mean position. Okay. Now let's say this first box has a surface area of 5 square meters. And then this next box has a surface area of 7 square meters. And this third one has a surface area of 4 square meters. Now I can compute an area weighted mean position. Right, so the box at 2 meters is 5 square meters. The box at 3 meters is 7 square meters. The box at 5 meters is 4 square meters, plus the total surface area, 5 plus 7 plus 4. Right, so the numerator would be meters cubed, the denominator meters squared. The answer would be meters. It would be the area weighted mean position of the 3 boxes. Okay, one more example. Let's say the first box is 7 kilograms. And the next one is 9 kilograms. And this one is 4 kilograms. Now we can compute a mass-weighted mean position. Right, so the box at 2 meters is 7 kilograms. The box at 3 meters is 9 kilograms. The box at 5 meters is 4 kilograms. Divided by 7 plus 9 plus 4 kilograms. So the numerator would be kilogram meter, the denominator kilograms. The answer will be the mass weighted mean position in meters. So mass weighted mean position is center of mass. Okay, and we did this example in 1 dimension. If I, let's say, move the box, say over here and here and here instead, and then if I knew, right, this was 7 kilograms and this was 9 and this was 4, and then now I know, let's see, both x and y components for the position, then I can get an x component of the center mass. You just add each position times the mass, and then like this, right? This is the x component of the center mass. the y component of the center of mass. And again, this is mass weighted. I could always change that to area. That would be the area weighted mean position, right? Or like dollars, dollar weighted mean position. And let's say you have, instead of 3 boxes, some object that looks like this. And then we split it into very small chunks, infinitesimally small, where you take the limit as they approach 0. So instead of discrete masses with discrete positions, we kind of use some calculus. So then the calculus version, instead of a sum, it's integral, right, like this. And these are differential masses instead. The y component, y. So we're integrating over the mass. So this would be the calculus version of the location of the center of mass. But we'll save this actual computation for another class. For this semester, we're going to stick to objects that would be obvious where the center of mass is, like a square, or say like a rectangle. The center of mass is right in the middle. Like here's a really skinny bar. The center of mass is just in the middle. Okay, so we're going to stick to shapes that just look like this. If you have some shape that looks like this, you'd have to integrate to find the location of the center of mass. So we won't do that this semester, just shapes like this. Now, why do we care? So, here, let's see. Let's say you have a box like this. And let's see, what's the gravitational potential energy of this box? And I have a datum over here. The gravitational potential energy is the weight times the height above the datum. The height of what above the datum? The height of the center of mass. So if the center of mass is here, this height, the height of the center of mass, that's the gravitational potential energy. How about kinetic energy? Let's say I throw this box. Oh, let's say it's a stick. I have a stick and I just throw it in the air. So it's flying through the air like this. Okay, what's the kinetic energy? 1/2 mv squared. The velocity of what? The velocity of the center of mass. Okay, the velocity of the center of mass. Although what's happening is this actual bar is rotating, so there's actually more to it. There's actually a rotational component to the kinetic energy, which we'll talk about that in another video. Okay, and then how about momentum? What's the momentum of this bar? The momentum is mv, mass times velocity, the velocity of the center of mass. And now, again, it is rotating, so there's going to be something called angular momentum, and we'll talk about that in another video. And then finally, what about force? Some force equals, right, time derivative of the momentum, which is this. And then what about when it's rotating? Then there's going to be an analogous quantity for force called torque. So that's like force, but rotating. That's torque. So we'll get to that in another video as well. Okay, so I just wanted to point out where the computation for center of mass comes from, but we won't really do too much of it this class. As long as you know the concept, then you're good. Okay, so see you on the next video.